Hi, everybody. Before I get started, I figured you all might like to see Frankie. She just woke up today and I'm bothering her a little bit, but I figured that this week was a good week to put her in front of the video camera. Um, this stuff that we're doing this week is a pretty important thing. I do expect these types of problems that you will be seeing, problems that have to do with the fundamental theorem of calculus and integrals and derivatives and the link between them. I fully expect there to be a lot of these types of questions on this year's 45-minute at-home open notes AP test. So if there were anything to practice, it would definitely be this stuff right here. Okay, let's jump into it. Okay, so like I said, for this fourth week of distance learning, what we will be taking a look at is fundamental theorem of calculus problems, or as I like to say, FTC problems. Talks about the link between integrals and derivatives and what you can use from each of them to say about the other one. So that's what all these problems have to do with. Before we get started on that, I just want to say that the theme for these types of problems is always be aware of what information you are given, and then think about what information you need to find. While it might seem that you can think about these problems in a formulaic way, you really cannot. You need to find that part of your brain that lets you think about what you're given and what you need to find, and just be ready to think about a lot of these types of problems. They really do, they're puzzles is what they are. I like them a lot. So let's take a look at the first one. So for this first problem, what we'll be doing is we'll be looking at the problem stem for 2016, but I won't be working out any of the A, B, C, or D parts yet. I'm going to look at a problem of my own design. I'm just calling them twist to tell you that I'm using the 2016 problem from your packet framework, but I'm just twisting up what a problem might look like there. So we've got here the graph of f, and it says the figure above shows the graph of the piecewise function f for -4 to 12, and the function g is defined to be this integral right here from 2 to x. So what we want to find in the twist problem is g of 8, g prime of 8, and g double prime of 8. Or say that one of them doesn't exist if it doesn't exist. So let's start with g of 8. Because g of x is the integral from 2 to x, g of 8 is going to be the integral from 2 to 8 of f of t. And because integrals mean area, we can essentially just treat this as finding the area underneath f from 2 to 8, which would look a little bit something like this. So this area right here is positive. It's because it's above the x-axis and going forward. The base of this triangle is 4. The height of this triangle is 4, and we divide by 2 to make a positive area of 8. And this area right here, for a very similar reason, it's a triangle again, because it's below the x-axis, it's actually going to be negative. So this area is -4. So the integral from 2 to 8 is going to be 8 plus -4, which is 4. So that's what g of 8 is. G of 8 is 4. Now g prime of 8, because derivatives and integrals have this inverse relationship of undoing each other, we know that g prime of x is actually equal to f of x, because derivatives will undo integrals. And if you want to get really fancy, you can think about the fact that technically there might be a chain rule here, because x is like an inside layer. But because the derivative of x is just 1, doesn't really change up the derivative at all. So g prime of x is just f of x or f of x times 1, however you prefer. So g prime of 8 will be equal to f of 8. And in this case, f of 8 is -4. We just read it directly from the graph. Okay. On the same token, g double prime of x is the derivative of g prime, which means that the derivative of g prime would be f prime. So g double prime of x is equal to f prime of x. So this is the slope of f. So when we look at our graph here, we look at the point at x equals 8, and we see that there's a cusp right there. So we know that because g double prime of 8 is the slope of f, or the slope of g prime, And because there is a cusp at that spot, we know that you can't find the slope at a cusp. So we say here that the G double prime of 8 does not exist because of a cusp. Okay, so that's domain 1. That's the kind of problem that you might see there. Let's take a look at what domain 2 has to offer. So domain 2 is all about what we call function analysis. And again, I'm going with the problem from year 2016 here. I'm going to specifically do parts A and B as written in your FRQ practice packet. So the figure above shows the graph of the piecewise linear function f. And then for the same thing, -4 to 12, the function g is defined by this integral right here. Now what I like to do immediately upon seeing that g of x is an integral is I like to write on the side, g prime of x has to be equal to f of x because derivatives undo integrals. And I also know that g double prime of x is equal to f prime of x, just like we saw before. So question A, does g have a relative maximum, relative minimum, or neither at x equals 10? Well, in order for a function g to have a relative minimum, something that looks like this, we see that g prime has to go from being negative to being positive. And on the same token, in order for g to have a relative maximum, like here, then g prime has to go from being positive to negative. So we need a change in signs. Now, if we look at this graph right here, which is the graph of f, which is the graph of g prime of x, at the point x equals 10, you can see that right before x equals 10, g prime, this graph, is literally negative because it's below the x-axis. And after 10, g prime, this graph, is also negative because it's below the x-axis. So there's no change in signs. So we would say that g has neither at x equals 10 because even though g prime of 10 is equal to 0, we see that right here, g prime of 10 is equal to 0. So even though there's a slope of 0 at that spot, g prime of x does not change signs. So that's all that's required of a justification. If you wanted a little visual of what the graph of g might look like from this, so from this information right here, the graph of g you would expect to be decreasing because g prime is negative, have a 0 slope, and then decreasing again. But drawing this picture is not a justification. You need to justify by saying something like g prime does not change signs, or g prime changes from positive to negative, or something like that. Okay, part B. Does the graph of g have a point of inflection at x equals 4? So x equals 4 is right here. Oops. X equals 4 is right here. And then that would be the spot on the graph right there. Now that looks like a local maximum of the graph of f or the graph of g prime. So remember, for g to have a point of inflection, in order for that to happen, g double prime needs to change signs. And g double prime will change signs when g prime changes from increasing to decreasing, or decreasing to increasing. So as you see in this graph, at x equals 4, we see that g prime is increasing right there, and g prime is decreasing right there. Remember, this is the graph of f, or g prime. So because g prime is increasing, that means g double prime is positive. And because g prime is decreasing on the second spot, that means g double prime is negative. So we do have a change in signs for g double prime here. So we would say, yes, g does have a point of inflection. And this is an important part because we're given the graph of g prime and not g double prime. We need to work g prime into our justification. Yes, g does have a point of inflection because g prime changes or switches from increasing to decreasing. This is the graph of g prime of x. It's what we're given. So the way that we justify our answer is by going off of what we're given. Yes, g double prime does change from positive to negative. You can say that, but you need to bring it back to g prime and say how g prime of x switches from increasing to decreasing. As we see right here, increasing, decreasing. Okay, let's take a look at what domain 3 might have for us. So domain 3 is pretty much just using the graphs of functions like f or g prime or g double prime to calculate some integrals and calculate some derivatives. So I'm using the 2016 model again here, but I'm doing a twist of a problem. You won't find this problem on the parts, but you can refer to this when you're doing problems out of domain 3 for other years. So here's our first one. Let h of x equal e to the 2x times g of x, and we want to calculate h prime of 0. So let's first find what h prime of x would be. So because I have e to the 2x times g of x, I need to do the product rule here. So the derivative of the first part, e to the 2x, is 2e to the 2x times g of x. The second part of the product rule will look like keeping the e to the 2x the same, and then taking the derivative of g of x as g prime of x. And then recall that because g of x is an integral, we can think of it this way. So 2e to the 2x times g of x plus, and then e to the 2x, and I know that g prime of x is just equal to f. So I'm going to write f of x right there. Now if I wanted to find what h prime of 0 is, we can just plug 0 into everything. So we have 2e to the 0 times g of 0 plus e to the 0 times g prime, or times f of 0. Either are fine. So 2e to the 0, e to the 0 is just 1, so this ends up being 2 times whatever we get from g of 0. G of 0 is the integral from 2 back to 0 of f of t. So the area underneath f from 2 back to 0, so it's going to be this triangular area right there. And this area ends up being -4. The area of the triangle is 4, but because we're going backwards and we're above the x-axis, that area accumulation is counted as negative. So that area is -4. So g of 0 is -4 plus. And then we have, again, e to the 0, which is just 1. And then we have f of 0, and f of 0 is +4, because this is the graph of f, and f of 0 is +4 up there. So altogether, we've got -8 plus 4, which is -4. So that's what h prime of 0 is. I heavily expect these types of problems to be on this year's AP test, the ones that have functions that look like this, e to the 2x times g of x or something like that, because you can't solve these problems using photomath or just Googling or something. You need to actually know what you're doing symbolically and abstractly in order to work these problems. You can't just look up what the derivative of e to the 2x times g of x is. So, okay, then our second twist problem, we want to calculate this integral right here, the integral from -4 to 0 of f prime of x dx. This is another abstract calculating problem, one that I fully expect to be on this year's AP test. Recall that in order to calculate an integral, you need to either find the area or antiderive and plug in points. Now you might think that we could calculate the area here, but this is the graph of f, not f prime. So we can't calculate the area from -4 to 0 because we'd actually be calculating the area under f instead of f prime. So we're actually going to think about this as an antiderivative instead. To take an integral, we find the antiderivative, and the antiderivative of f prime is just f of x. Because when you derive f, you get f prime. When you antiderive f prime, you get f. So we're going to antiderive to f of x, and then we're going to plug in 0 and -4. This is going to be f of 0 minus f of negative 4. F of 0, as we saw before, is 4. We read it directly off the graph up here. And then f of negative 4 is negative 4. So 4 minus negative 4 ends up being 8. And there we go. You probably saw that integral and didn't think it was going to be super simple, but for these abstract ones, it really can be. You just need to keep in mind that this is one where you should be anti-deriving, because the antiderivative of f prime is just f. And we have the graph of f right up here. All right. Let's take a look at some harder problems, ones that you might not have expected to see on these types of fundamental theorem of calculus problems, ones that specifically have to do with absolute maximum and absolute minimums and things of that nature. So before we get started with absolute maxes and minimums, let's recall what an absolute max or min actually is, what that idea means. So in an absolute maximum or absolute minimum, the function might be going from one point to another point. And then if it's on a closed interval, like it is right here, we certainly have some places where the function is at its absolute highest and its absolute lowest point. And I want you to note where these points could be. We have some local mins and local maxes, like right there and right there. But our absolute max and our absolute min, so absolute extrema, can occur in either of two places. Our absolute extrema could occur at the endpoints of the interval, which would be either endpoint A or endpoint B, or at critical points, when the derivative or when g prime is equal to 0 or undefined, which are these humps and things in the middle. So what we'll end up doing here is we will end up making a chart to test these different candidates and see which of the candidates is the absolute highest point and which is the absolute lowest point. Okay, so let's take a look at our function here. So we still have the same thing. G of x is the integral from 2 to x of f of t. And then we've got a little candidates chart that we're going to make. We have an x value, I'm going to have a g of x value, and then because I know that 2 of my candidates are the endpoints, and I know that my interval is going from negative 4 to 12, I'm going to put 2 of my endpoints right there, negative 4 and 12 as x and y. Then I also need the critical points, so where g prime is equal to 0, where g prime is undefined. Now remember that if g of x equals the integral, g prime of x is equal to f of x. So this is the graph of g prime up here. It's f, yes, but it's also the graph of g prime. So where is g prime equal to 0 or undefined? Now I might think that g prime is undefined at a whole lot of places because we've got all these cusps right here. But g prime is defined at those spots because g prime of 0 is 4. G prime of 4 is 4. These are cusps of g prime. So g double prime would be undefined at those spots. G prime is equal to 0 always where it hits the x-axis in these spots. So these are all of our critical points that we're going to put on here. So we've got negative 2, 2, 6, 10, and then 12 is our endpoint. So we've got a lot of things to test right here. Now, if we want to find the absolute minimum and the absolute maximum value of g, what we're going to do now is plug these points into our literal g of x and see what that gives us. So to find g of 4, we're going to use our integral function, what we were given for g over here. So from 2 to 4 of f of t. And then because integrals mean area, we can look up at our graph of f, our graph of g prime, and find the area going from 2 to 4. So the area from 2 to 4, oh, excuse me, negative 4, it's going backwards. Okay, from 2 to negative 4, going back like this. And then down like this. Now, I already know what the areas of these triangles are because I've done them before. You might not have if you're just timestamping to this point. The area of this triangle here is 4 long, 4 high, divided by 2. This is going to end up being 8, but because it's going backward, we say -8. So this will be counted as a -8 area. And then this, yes, it's below the x-axis, but because we're going backwards, it's going to be counted as a +4. So this is going to be -8 plus 4, which is -4. So g of -4 is -4. Let's take a look at g of -2. By finding g of -4, we've already sort of found what g of -2 is. G of -2 is just going to be this area right here, going backwards. So I know that that's going to be -8. It's the integral from 2 to -2 of f of t dt. G of 2, that's just going to be the integral from 2 to 2 of f. And that's really easy. That's just 0. If we go to 6, we're finding the area going this way, and that's forward and above, so it's going to end up being positive. So because this is a 4 by 4 divided by 2, we have an area of 8. G of 10 will be this triangle plus this triangle right there. So positive area of 8 plus a negative area of 8 will give us an area of 0. And then 12 adds in this little negative area right there. So we have, 8 plus -8, and then -4 again, which puts us at -4. So it looks like we have 2 pretty clear-cut absolute maxes and mins right here. Our -2, -8. This is going to be our absolute min, which is g of -2, which equals -8. And then our absolute max happens at x equals, it looks like x equals 6. And g of 6 equals 8, according to our candidates chart. All right, that's how you find absolute maxes and mins from these FTC problems. Let's take a look at what comes next. Okay, so the next 2 problems will be challenging problems from domain 1 and domain 3. You can expect these types of problems, as well as the absolute max and min problems, to appear in subpaths C throughout all of the domains. So yeah, so I'm using the 2017 STEM here, and I'm specifically doing question A from these. And this problem is a little bit given. We're a little bit different, excuse me. We're given the graph of f prime instead of the graph of f, and then have an integral or something like that. And it says that the function f is differentiable on the closed interval -6 to 5 and satisfies f of -2 equals 7. So we know that f of -2 is 7. Now, if you look at this graph and think that's not true, f of -2 is 0. Remember that this is the graph of f prime. The graph of f is something that we can't see. We're just told that f of -2 is 7. So, the graph of f prime consists of a semicircle and some line segments as shown in the graph above. And we need to find f of -6 and f of 5. So we need to work backwards by going from f prime back to f. Now, the way that this kind of thing works is it works by using the fundamental theorem of calculus, funnily enough. So the concept behind it is this. Remember that the integral from a to b of f prime of x is just the antiderivative of f prime, which is f, with b and a plugged into it. So f of b minus f of a. In that respect, if you wanted to actually calculate what f of b was, you could just move f of a over to the other side, and you'd get that f of b equals f of a plus, and then the integral from a to b of f prime of x. This is like that thing we explored back in January where we talked about how you can find the ending position of a particle by taking the initial or the starting position plus the displacement. That's what this is. F of A is like the initial position, and then this integral, the integral of F prime, is like the displacement of the particle, if you prefer to think of it that way. This is the thing that we will be using to calculate F of -6 and F of 5. So according to this relationship, F of -6 is going to be equal to, and then because I'm given this information right here, F of -2, I'm going to use F of -2 to set up an integral that goes with it. So F of -6 is my starting point, F of -2, plus the integral that goes from -2 to -6 of F prime of x dx. And I can plug some numbers into this because I do have some information. I know that F of -2 is 7. And then the integral from -2 to -6 of F prime is this area right there. That area is above the x-axis, but because we're going backwards, it's counted as a negative area. So the base of my triangle is 1, 2, 3, 4, and my height is 2. So 4 times 2 times 1/2. And because it's going backwards, it's negative. So this area will end up being -4. So F of -6 has to be 7 plus -4, which is 3. So F of -2 was my 7. This integral right here ended up being -4. In the same token, we can find F of 5 by setting up again the starting point, F of -2 plus, and then the integral going from -2 to 5 of F prime of x, the initial position plus the displacement. So F of -2 is 7. And then the integral from -2 to 5 is this circular area right there. And then that's 3, 4, 5. 5 is right there. So we got this triangle right there. So my circle has a radius of 2 and is below the x-axis going forward. It's going to have a negative area. That negative area will work out to be something like, let's see, 4 pi divided by 2. So -2 pi. It's a semicircle, so I'm doing the area of the whole circle dividing by 2, then putting a negative on it. And then I'm adding in this area of the triangle. So this triangle right here has a base of 1, 2, 3, and a height of 2. So that area will be 3 times 2 times 1/2, which is 3. And we don't need to simplify any of this. We are perfectly okay to just write down 7 minus 2 pi plus 3. But if you want to, you can write 10 minus 2 pi. That is totally fine. All right, so that's how we move from F prime to F. We use integrals to do that. To go from F prime back up to F, we need to use integrals. All right, let's take a look at our last twisty, challenging problem that I'm using the 2017 STEM for. All right, so I'm using the same 2017 STEM. I've got this graph of F prime, and it satisfies F of -2 equals 7. And then we've got the graph up here. What I want to do in this twist problem, you won't find it in the 2017 thing, but I'm just doing it as an example, is we want to calculate the integral from -2 to 0 of F double prime of 3x. Now remember that in order to calculate integrals, you either need one of two things. You need to find area, or you need to antiderive. And because this is the graph of F prime, not F double prime, we can't be finding area here. This is the area under F double prime, but I have the graph of F prime. So I don't have the graph of F double prime. Can't find area under F double prime if I don't have F double prime. So area is out. But we can antiderive. The antiderivative of F double prime will be something like F prime. But there's a twist. Because I've got this 3x right there, we really want to be thinking about u substitution. I'm going to pick u equals 3x. And then my dx is going to be du over 3. And what we end up with then is we end up with 1/3 the integral of f double prime of u. And then I already pulled out my 1/3, so I just replace the dx with du. And then the integral of f double prime of u, du, is just the antiderivative of f double prime of u, which is just f prime. Oops, I wrote 1/2. So this will end up being f prime of 3x. And then we're plugging in our bounds, -2 to 0. I didn't write my -2 and 0 right here because this is a u integral, and these were x bounds. So I don't plug in my x bounds until I've got my integral back in terms of x again. So I'm not writing them here because I have u's, but now I have x's back. So I'm going to put my x bounds in, just trying to be mathematically clear. And I can plug these things in. So I have 1/3, and then I can find f prime of, I plug 0 in, I get 0, minus. I plug in -2, I get f prime of -6. And what that ends up with is 1/3. This is the graph of f prime, so I can directly look up and see what f prime of 0 is. Looks like f prime of 0 is -2, minus, and then f prime of -6 is 2. So when I do the subtraction here, I end up with 1/3 times -4, which is -4/3. So there we go. That's our integral. The big pattern to see here is the pattern know that when you antiderive f double prime of 3x, it's still that little simple u substitution pattern that will put the 1/3 out in front because we're doing the reverse chain rule. If we were going forward with the chain rule, the derivative of the inside would be 3. But because we're antideriving, a 1/3 gets put out front. And then we antiderive with the inside kept the same. That's the big pattern to notice from this sort of calculating problem right here. Okay, that's all the tough stuff that I've got to do with FTC problems. Remember that in all of these, what you need to do is start with what you know, and then try to link that with what you know you need to find. Don't think of any of these problems as formulaic, but think about really what the concepts of what integrals and derivatives mean and how those concepts can help you find the solutions to these puzzles. Okay, that's it. Have a great day, guys. Thanks. Bye.